So this is lesson 3 for Unit 2. We're going to take a look today at functions and see whether or not they're continuous or discontinuous. And it's the last lesson before we finally get into doing some full-on serious calculus. But we are going to take a look at how we can describe whether a function is a continuous function or a discontinuous function. And in a layman's sense, if somebody says, oh, it's continuous, they mean that there are no breaks in the function. And if it's discontinuous, well, then there's some sort of break in the function. Another way I've heard it described, this is a very casual description, it's not the perfect definition, but I've heard it described this way. A function that's continuous is going to have, well, it won't have any pencil lifts. So if you're drawing it, you can take your pencil, draw the graph, and you won't ever have to lift your pencil up off the paper and then put it back down in a different spot. But if it's discontinuous, then there's some sort of pencil lift going on where you have to draw the function and then go, whoa, 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 pick your pencil up and maybe move it a little bit and then put it back down. Now, that's not an official math definition. We're going to look at the strict definition right here. And I've got a function that definitely has some discontinuities in it. And I'd like to just focus our thoughts here at this spot right where x is equal to 2, just for a moment. We're going to look right here, pick that x value, kind of see what's going on there. And trying to figure out like why a mathematician would say, oh, that function's not actually continuous there. For it to be truly continuous, then this has to be true. Okay, and it's in this box down here underneath the graph. It says if f of x is continuous at some point, x is equal to a, so that's where I am right here, right? This is my x is equal to a. I guess a is equal to 2 for the moment, just while I stare at it. Then this has to be true. The limit of the function as you approach a from the low side, from the left side, has to be the same as what the function actually is at the point. No limit there at all. And that has to be equal to the limit as you approach that x value from the high side, from the right-hand side. Right, so we have this left limit, this left approaching limit, and we have this right approaching limit. And we want to make sure that those two limits are the same and that they're actually equal to the function when you get there. So let's take a look. The left limit, right, as I come in from the left side, let's draw this in green here. So I'm going to be following this function, coming in from the left, approaching 2. That would mean saying, hey, what y value are we heading towards as we come along the graph like that? Okay, what y value does it look like we're going to be getting to right as we get to 2? That's what that limit is on the low side. On the high side, way over here on the far right of this box, that would say, well, what if you come in from the higher than 2 side and ask yourself, what y value are you approaching when you get there? So these two limits, okay, this one here, this lower left limit, and this upper limit, this right limit, they're asking, where was the function heading? Where does it look like it's aiming for? Those have to be the same. They're clearly not in this picture, but those would have to be the same. And then you ask yourself, well, where does the function actually go? When you actually get to the moment when you're at x is equal to 2, where is the function? Well, it looks like this particular function, if I find the little dot here, it's actually sitting right there. Okay? So this part right in here is saying, well, where did the function actually go? So it takes these two green issues in order to ask the question, where was the function heading? And then that one issue I've got in the center to figure out where it actually goes. And so to put this into words, if I want to take this math definition that's down here and say, okay, well, what is that saying, just in everyday language? I guess you could put it in words this way. If it's going to be continuous at some sort of point, right, x equals something, here I'm doing x equals 2, then the function goes, right, its y value goes where it looked like it was going to go. So there has to be total agreement on where it looked like it was going to go. Those two limits would have to be the same. They're not here. And it would actually have to be there. And if all three of those things are true, approaching from the left, approaching from the right, and then where you actually are, if they're all the same, then you can say, oh yeah, at that spot, this function is continuous. So we're going to try this out at 4 different spots on this graph right here, right? At x equals -2.5, at -2, 1, and 2, and take a look and see whether by this test it's actually continuous or not. So for the first column, we're going to be looking at the function at -2.5. So that's actually at this x value right there. And let's take a look and see if all 3 of these things are the same. Now, I'm gonna skip the first row for a minute, and I'm going to jump down to these 2 limits, right? What's the limit of the y value when you approach -2 from that low side? So this is saying, yeah, can you go and look on the low side, the left side, and then the next box down, we're going to say, well, what if you approach from the high side, from the right side? Then what y value are you heading towards? Okay, well, let's go look at the graph. Okay, so I look at the graph here to see what y value we're approaching as we come towards -2 from the left side or from the right side. Actually, there's some pretty good agreement there. It looks like both of those are heading towards, both those limits are heading towards a value of 1. Okay, so far so good. Because if we want this to be continuous, then these 2 things must actually agree, right? So if those match, then I can come up with a decent answer for this. What's the actual limit of the function? Not left, not right, just full-on limit. As you approach -2.5, well, they both agree. They're both saying 1, so I could say, oh, the limit is 1. We're definitely heading towards 1. Okay, well, that top box says, hey, let's actually look at the function. Let's look at the y value, right? It's like the center part I had there in red. What is the actual value for the function at -2.5? Well, this graph doesn't even have an answer. It's like, I don't know, and it just disappears for a little while. So if people ask you, well, what is the value of the function then? You'd have to say, well, it doesn't even have one, right? The answer is it does not exist. And you would have to have all of those things agreeing, right? This number and that number, they would have to agree in order for us to say, oh yeah, it's continuous. And I don't see any agreement there. So I would say, oh, it's too bad, but this particular graph is discontinuous. Okay, at that point. Well, let's check out the point -2 and see what's happening there. And I want to start it with the second row again. Let's go with the limits first. So looking at -2. Okay, so now we're going to be, let's get that one out of the way a little bit. We're going to be approaching this -2 from the left side. We're going to come in from the right side. Whoa, looks like there's lots of agreement there. Okay, let me just zoom in on that. Right, as I approach -2, yeah, everybody seems to agree on where we're heading, and we actually even go there. So I've got all 3 of those things in line. They're all apparently hitting this value of 1/2. All right, so let's put that in down here. We can say, okay, if you're going to be looking at the point x equals -2, both those limits, both from the left and from the right, they seem to be in agreement. They're 1/2 and 1/2, or 0.5, whatever you want to call it. Both of those agree, so I'm happy that both of those agree. I actually have an answer now for this. The limit's just 1/2. And then the actual value of the function. You know, what happens when you get there to -2? Well, the function actually goes where it looked like it was going to go. It goes to 1/2. And since everybody's in agreement, right, that number is matching up with that number, and the only way that the limits can say it's 1/2 is if both left and right limits agree, and they did. So now when people say, well, what do you think about this one? I would say, oh, that's great. This thing is totally continuous at x is equal to -2. It actually went to 1/2, and it was heading towards 1/2. Okay, let's try x is equal to 1. Let's go and look at that y value. All right, we're going to think about what happens when you approach x equals 1 from the left, and we're going to approach from the right. Looks like there's agreement there. Both those approaches are heading towards the same y value of -1. But when you actually get to x equals 1, the graph skips up to here, up to a y value of 1. I don't know why it does, but that's what that graph seems to be doing. So my answer for this, kind of thinking this through, you know, people are asking me, is it continuous? Like, well, let's check the limits first. Both from the left, we were heading towards -1, and from the right, we're heading towards -1. Beautiful agreement there. Okay, so if people say, well, is there a limit? You bet there is. We're limiting to -1. And then you ask, did it go there? No, it actually jumped up to +1. Okay, so there's no perfect agreement on where it looked like it was going to go and then where it actually went. So you would have to say, too bad. At that point, the graph is discontinuous. Okay, one last scenario. Let's go and take a look at that x is equal to 2. Kind of talked about that at the top of the page. Here, when you approach from the left and from the right, the limits don't even agree. There's not even any agreement on where the function looked like it was going to go. And then we see that it does actually go to 1. But as I approach this x equals 2 from the left, I'm heading towards a y value of 1. And as I approach x equals 2 from the right, I'm heading towards a y value of 2. So this limit problem is going to definitely say this thing is not going to work, right? I've got a 1, I've got a 2. I don't have any agreement there. So people said, hey, what do you think about just the limit? Well, there's no agreement on left and right. So the limit itself just does not exist. And then if I go and check out what the function's doing, not that it much matters now, this thing is already done. But if I check out what the function's doing, well, it's a 1, right? It was, trying to work with that left limit, I guess. But the right-hand limit wasn't in agreement. So you would have to say, oh, no, this is a discontinuous function at that point. X is equal to 2. So we've actually seen in that graph up there, a few different ways that things can be discontinuous. Let's take a look a little bit more at how we can describe why a function might be discontinuous. And some of these discontinuities might be fixable, and others are actually just not fixable at all. So at the beginning, I want to just point out that graph A is beautiful. Graph A has every single point being really nice, right? It's just beautifully continuous everywhere. It's just a nice line. And certainly if I was to go and look at this point at x is equal to 0, I don't see any problem there at all. So if this section of your notes is to talk about different types of discontinuities, well, that just isn't one, because here this thing is continuous. But the next two graphs, graph B and graph C, these f of x's, these functions, they have some discontinuities at x is equal to 0, right there at the y-axis. But the good news is these ones are fixable. So I'm just going to put a little box around this here and say, hey, there's a problem with these. Yeah, I get it. But the good news is we're actually going to be able to, we'll see at the bottom of the page, fix this and turn it into a nice continuous function. So maybe just a little note in here. For these two, these are, fancy word in math is removable. The problem is removable. In other words, the discontinuity is, it's fixable. With a little bit of work, we can patch the hole. So why is the first one there? Well, the first of the two that we're looking at. Why is B some sort of discontinuity? Well, there's a name for that when the graph just disappears for a moment and then it comes back later on. You would say, well, it's got a discontinuity there because it's got a missing point. Okay, seems like a reasonable name. And for C, well, the point's there, but it's just in the wrong spot. It's kind of all off on its own. So this might be called an isolated point. That's why it's discontinuous there, because it has this little all off on its own isolated point. We can fix those ones. We will not be able to fix these three. So again, I'm just going to put a big kind of box here around these three, just kind of group them together and say, hey, watch out for these ones. These ones here are not fixable. So math people would say they are not removable. The first graph is cruising along at y equals 0, and then it just goes boop and jumps up to x is equal to 1. It's actually a very, very well-known function. The name for why it's a problem, let's get that right first. Okay, this would be sometimes called a step discontinuity, or people might call it a jump discontinuity. And that particular function that goes from 0 to 1, Well, you'll see this one when you're playing around in physics and in engineering. That function was famously invented by this person here. He's got kind of an interesting haircut. His haircut kind of looks like the function. Just kind of goes and jumps up like that. This is Oliver Heaviside, and he actually did a lot of neat, electrical engineering with functions like this, because he said, hey, I can use that function to model somebody turning on a light switch. The light's off, 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 and then the light goes on. And you can actually use those functions to, in electrical engineering, model things that are being turned on, whether it's a light bulb or a heater. The next discontinuity, if you graph this next one, just on your graphing calculator, you'll see that it kind of looks like a tree. It kind of goes way up to the sky and then comes out of the sky like this. All right, it's not perfectly graphed, actually. It probably should go through the point 1, 1, and 1, -1, but it's close. Kind of get the idea there, like that. Oh, that looks even worse. Let me try that again. Okay, I'm going to go with that. So this thing right here at x is equal to 0, like, okay, what's going on there? Why is this graph not working? Well, it's heading to the sky. It's just going up to infinity. And at x equals 0, the function doesn't exist. So it's heading to infinity, but then goes nowhere at x equals 0. So this is an infinite discontinuity. You can't fix that. You can't turn this into, you can't turn this into a continuous function by repairing that at all. And this next one, it's a graph of sine, but instead of just the sine of x, which would just wobble beautifully, it's the sine of 1 over x. And 1 over x gets really big. It moves very fast when you get near the origin. And so this graph of sine that normally just kind of, wobbles around between 1 and -1, all of a sudden starts to go just silly like this. And then it sort of unwobbles again later. And so the question is, well, if I was to try to figure out what the function's doing right here at x is equal to 0, what's happening? And the answer is, I don't know. It's moving around so fast that we can't even figure out where it is. So that could be what we would call an oscillating discontinuity. Okay, well, those first discontinuities, the ones that are removable, we can actually fix them and make that function look nice. We can turn that broken f of x into a nicer repaired function. So let's see if we can do that down here. So this section here says, yeah, the graphs of b and c, okay, the two up there at the top of the page, the graphs of b and c can be made continuous by carefully fixing the y value right at that problem, right at y equals 0. We can't fix the other ones. We can't fix d, e, and f, but we can fix b and c. So example 1 says, give a formula for the extended function. It's like, okay, well, what's this story about extended functions? What's that all about? That just means the repaired version. Okay, so we're going to repair it and make this thing continuous. And when we do, it will no longer be the same function. Right? It'll be a brand new function that's a little bit better. And so I need to give it a new name, right? Because it's not the same function anymore. I'm kind of happy with the old function most of the time, right? Like I'm looking at these graphs for B and C. They looked pretty good. Cruising along here is a nice straight line. And then, whoa, we had either a missing point or an isolated point. And what we need to do is we need to go and fix that by kind of patching the hole. Like here we have to go and put a point in. And here we need to say, no, we don't want that one. We want to put a point here. And so that's actually pretty easy to do. What we'll do is we'll say, well, you can graph f of x most of the time. So all the time when it wasn't the problem, let's just go with the original picture. But at the moment when it's a problem, right at x is equal to 0, when this thing was causing us troubles by either being missing or a little isolated point, let's go and patch the hole. And it looks like the y value that we needed to have in there, should have been a y value of 1. So we'll just say, yeah, let's make the function equal to 1 at the moment when we have that trouble. So normally the function, but then we'll patch it and put x equals 1 in there. Or I guess you could come up with, the equation of this line, right? You could look at it and say, hey, why don't we just talk about this line? It's a line with a y-intercept of 1 and a slope of 1. Another option, you could have said, hey, here's my repaired version, g of x. This would be the original function, but with the repair. You could say, yeah, it's just like 1x plus 1, right? Slope of 1, y-intercept of 1. Yeah, that would have worked too. just a description of the picture with the hole being repaired. Example 2, a little more interesting. Give a formula for the extended function of that is continuous at the point x is equal to 3. I'm going to graph this one just to kind of see what's going on. Why is this thing having troubles? I'm going to put my numerator in a bracket here, so I've got x squared minus 2x minus 3 divided by x squared minus 9. And I'm going to try zoom 4 right off the start. And they apparently are worried about x is equal to 3. Oh yeah, okay. It's a little hard to see, but I think this graph does actually have an issue there at x is equal to 3. There's just a little missing point, right? And they're like, yeah, can you fix this? Can you come up with a graph that will look like that but without the hole, right? That's the extended function, the better function. So I need to know what the y value is right there. And then I can say, yeah, just go with this y value. Because this function here, this f of x, is definitely busted there. It's just got that missing point. Well, maybe I can do that by doing a limit. Let's do a limit of that function as x approaches 3. I'm going to take that function, do a little factoring. I've seen that can be super helpful trying to figure out what the limit is. The top one factors x minus 3, x plus 1. And the bottom one factors x minus 3, x plus 3. Now remember, we're never going to let x actually equal 3 if we're doing a limit, right? If that's our plan, if this is what we're doing, x won't be 3, it'll just be really close to 3. So you can be pretty happy coming in and saying, hey, why don't I just cancel this off? It's the same value and it isn't 0 if I'm doing a limit. So I'm trying to do the limit now of just these two binomials divided by each other when x is 3. I'm nowhere near negative 3, that would be a problem, but I'm near 3, so I can do direct substitution. I'm going to have 3 plus 1, that's a 4, and then 3 plus 3, that's a 6. So I've got an answer of 4/6 for my limit. I can reduce that, of course, and call it 2/3, but yeah, it looks like 4/6. Let's just see if that looks right. Okay, tracing along here. Let's see what happens when we get close to 3 and see if it is consistent with being 2/3. Okay, so 0.661, nothing at 3, and then 0.672, yes, okay, so graphically too, it looks like it's consistent with 2/3. So I need a new function, a repaired function. You can call it whatever name you want, but I just wouldn't call it f of x because it's not the same function anymore. Maybe I'll call it repaired x, right? Repaired function. And I would say, hey, why don't you just go and graph f of x most of the time? Go with the original graph. Just graph that only when x is not 3. But when x is 3, we better have a new plan. You better fix that little missing hole. So let's go and graph 2/3. There's actually another option. You could look over here and say, well, why don't we just go with that x minus 3 factored out? So a different way to draw that same repaired graph would be to say, hey, why don't we go with x plus 1 all on top of x plus 3. That would be the same graph, but not have the hole. In fact, let me just show you here. I'm going to put this in as a, oops, I didn't mean to do that. I'm going to put that back in there. Push the wrong button there. X squared minus 2x minus 3 divided by x squared minus a 9. Okay, so let's make sure that's working. And it's got the little hole right there, 3. Yep, great. Okay, now I'm going to put a different function in. How about here I put in my new repaired one, x plus 1 divided by x plus 3. And I'm going to tell it, hey, graph this one thick, just so you can see what happens. It's going to draw the exact same graph and no hole, right? So it's kind of a repaired version. So yes, some of those discontinuities are repairable. And up until this point, we're just talking about, is a function continuous at a point, right? Here we're worried about x is equal to 3. Now on the next page, we're going to say, well, what about an interval? What about a section of the number line? Okay, that's all we mean by interval here in this, in this context. Okay, so just going to put in here a section of the number line. That's what this interval is all about. So if you want a function to be continuous on some section of the graph, That's only going to be true if and only if, we would say in math, which is sometimes abbreviated as IFF, kind of a new word. Okay, all definitions are if and only ifs. So it's going to be continuous on a section of the number line if and only if it is continuous, the graph, I mean, the function, at all of those x values in that interval. So here's where we're going with this. We've already got a good description of what it means for a function to be continuous at a point, right? It's got to go where it looks like it was going to go. But now we want to talk about, well, is it continuous on a whole section of the number line? Well, it has to do all of that perfect continuity at a point, but at every single point. So for example, let me just zoom in here a little bit on this graph, make it a little easier to see. I know this graph, we've seen it on the other page, has some issues at certain spots. But what if I picked just one section? Like what if I said, oh, I'm really only worried about the section from -2 all the way to 0 for x? Well, I could go and look and say, all right, checking this graph out from -2 all the way up to 0 for x. So that would be all along here. Hey, that graph was fine. There was no issue. I could check out every single one of those points on that little pink section, and it would be fine all day long. So yeah, that would be continuous on that section if that's all you want to talk about, if that's all that concerns you. So yeah, I'm going to put a little note in here. For example, in this graph here, f of x is continuous on the interval. And now I'm going to give people a description of that section of the number line for x. From -2, including -2, all the way up to and including 0. So if people say, well, what about this function? Is it continuous on this section of the number line? Just looking and say, okay, for every point, would it actually be okay? So that's continuous on a section of the number line. But what if we just use the phrase, oh yeah, continuous function? So now we're kind of getting really big picture. We're not saying, well, that graph, is it continuous at x is equal to 2? And we're not saying, well, is it continuous from -2 to 0? But what if we just say, oh yeah, the graph is continuous? Here's the definition, and there's a part of it that may surprise you a little bit, okay? But we're going to say a continuous function, if that's all you want to call it, is one that is continuous at all x values. Oops, kind of forgot the x and x values. Try that again. You know, it's got to be continuous everywhere, right? If it's continuous on this big giant interval of everything, then we'll say, oh yeah, it's a continuous function. But then math people looked at it and said, well, hang on. What about a graph like this one? What about a graph of y equals root x? Are we going to say that that one's continuous? You know, I can take my pencil and I can go, okay, here we go, and I can draw it like that. You know, is it a continuous function? People would say, yeah, it looks great. There's no pencil lifts. You know, everything is fine. And then people might say, well, you said it was going to be continuous at all x values. If this is a continuous function, what about these x values here? What about -3.5? And it's like, well, the graph's not even being drawn there. It's like, well, you said it was continuous at all x values. And it's like, well, okay, we got to be fair to this thing. And if the graph's not even happening there, then I guess it doesn't have to be continuous there. You know, and then what about this endpoint right here? You know, is there a limit from that left side? Well, no, it's an endpoint, right? So you got to kind of cut that thing a little bit of slack. And we're going to say, well, maybe we need to relax this definition a little bit and say a graph is going to be a continuous function if it's continuous at all x values where the graph is happening, right? So they add this on. They say in its domain. You know, where the graph is actually being graphed. And then people went, whoa, wait a minute. What about this graph? What about the graph of 1 over x? Okay, when you graph it, it looks like this. Is this a continuous function? And people go, I don't know, let's check it out. You know, we can try out a few different points. You know, is it continuous at 2? Yep. Is it continuous at 2.5? Yep. Is it continuous at 3? Yep. Is it continuous on this section from 1 all the way out to 4? Yeah, okay, it's continuous on that interval. But is it just generally continuous? I can't draw it without lifting my pencil. So I'm kind of looking at this definition here now going, okay, well, what does this say? It has to be continuous at all x values in its domain. And it turns out we're going to look at it and say, well, yeah, it meets the test. Just like the square root of x, that's a continuous function. So a little weird, but we're going to say, yeah, these ones here as examples, these are both, not just the one on the left. These are both continuous functions. Now I know what you're thinking. You might look at this and say, well, hang on, what about at x is equal to 0? That 1 over x graph is not continuous right there at x is equal to 0. And I would say, I agree with you. That graph of f of x is not continuous at x is equal to 0. It's also not even continuous on the interval from -1 to 1. But I'm still going to call it a continuous function. And again, people might go, what about x is equal to 0? And I'm like, why are you talking about x is equal to 0? That's not in its domain, right? It's not even part of the function. So if we're just asking ourselves, is it a continuous function? You're not even allowed to look at x is equal to 0. You could look at x is equal to 0 if people get specific and say, hey, is it continuous at the point x equals 0? Then you'd say no. Or is it continuous on the interval from -1 to 1? No, because it's not continuous at 0. But it's still a continuous function, right? It's just the way the mathematicians wanted to describe it. That way we can talk about graphs like root x and say, yeah, that one's fine, because it has a whole section where it's not working. Okay, combinations of functions. I've got my little old school math guy here. Here's a little rule for you. If the functions f and g are continuous at some point, x is equal to c, then if you make combinations of those functions, you're going to find that they're also continuous at x is equal to c. You can add things that are continuous. You can subtract things that are continuous, multiply them by constants, divide, as long as it's not division by 0. All of those things you can do, even making functions inside functions, they're going to be still creating a continuous picture. So maybe I'll put this in nice simple words here and say, you make continuous functions doesn't look right. Oh yeah, okay, sorry. Questioning myself there on the spelling. You make continuous functions when you build them from continuous functions. I'll say when you build using continuous functions. So for example, this question here, it says, oh, can you do this limit of some really complicated thing with absolute values, and there's trig in there, and x is going to pi over 2, and I'm a bit intimidated. Like, I'm wondering, like, how am I going to factor that? But then I can start tearing this apart, and I can start imagining all the different things that are being used here. Like, for instance, let's just zoom in a little bit. What about just the x that's being multiplied by sine x? Just this part right there. Is the graph y equals x continuous? The answer is yeah, sure, you bet it is. Okay, what about the graph of sine? If you just graph sine, is that continuous? Yeah, it kind of does like a little wobble, but it's continuous. Okay, so if x is continuous and sine is continuous, then when I multiply them, that's what this says up here in rule 3, that'll be continuous too. So the whole numerator is continuous. What about the graph of y equals x squared? Yeah, that's a parabola, it's continuous. What about the graph of y equals 2? Yeah, it's continuous. What if I add them? Yeah, that's rule number 1. Okay, so the denominator is continuous. What about that fraction, top divided by bottom? Well, it'll be continuous as long as the bottom isn't 0, and it won't be 0 at pi over 2 for x. So that whole thing inside the absolute value is continuous. And generally, the graph of absolute value kind of looks like a V shape. It's continuous too. So I've got a continuous function inside a continuous function. I've got, actually, like one of everything here, I've got a sum. Well, I don't have a difference. I've got a sum, a product, I'm doing a quotient, I got a composite, got a lot of things going on there. And here's what I know, that this thing right here, I don't even need to graph it. That's going to be continuous. It's going to be continuous, especially at pi over 2. So if I needed to go and do this limit, I would feel totally comfortable simply doing direct substitution. I would say, let's just go and substitute the value in. Okay, you're allowed to do that for continuous functions. And I know it'll be continuous. If anybody questions me, I can say, hey, look, I made it out of continuous things. So let's just go and do direct substitution. We'll go and do the absolute value. Now we'll substitute in pi over 2 for x. Okay, you got to know your special angles. Pi over 2 is the same thing as 90 degrees. Pi over 2 squared add 2. Okay, well, sine of 90 degrees is just a 1. So we're going to end up with pi over 2 in the top divided by, not much more I can do with the bottom except maybe call it pi squared on top of 4 add 2. Okay, I can leave it like that. I could multiply top and bottom by 4, might make it look a little bit nicer. And I don't even have to worry about these absolute values because everything's positive, right? So if I multiply by 4, I'm going to have 2 pi sitting on top of pi squared plus 8. And if people go, are you sure it was okay to do that direct substitution? Yeah, because it was a continuous function. And I know it's continuous because I made it out of continuous things. And that takes us to the very last page for today. And it's the first of a number of theorems that we're going to have for AP Calculus. You've got your little study guide sheet here. Oop, bring that back up. And on the back side of your study guide that you got at the beginning of the course, the back side are just a whole bunch of theorems, little rules that you can be confident knowing will work every single time. And one of them is this intermediate value theorem. So let's go and take a look at exactly what this intermediate value theorem is trying to say. If you're somebody who's thinking, oh, I don't know what I want to do for a career, I don't know whether I want to go into math because I like it so much, or maybe into law, I might want to be a lawyer, then you will love the theorems. They are for like math lawyers who are trying to argue something in math court, and they can just keep throwing these theorems down. It's kind of like name dropping, right? It's like, whoa, you know the intermediate value theorem? It's like, oh yeah. So let's start tearing even the title apart. Okay, so it's called this intermediate value theorem. The word intermediate in this context, it's going to mean in between, right? That's what that's all about. So I'm going to put this in common language. This is the in between, and then value, right? When they're saying, oh yeah, there's some sort of value, well, that's actually going to be a y value. So this is the in between y value. And then theorems are just rules. So when they say, oh yeah, it's a theorem, okay, great. It's some sort of rule that I know is going to be true every single time. So if people say, oh yeah, I'm going to be talking about the intermediate value theorem, they're talking about the in-between y value rule. That's all it is. So I've got a little spot here where you can draw a graph. We're going to just see the intermediate value theorem unfold right in front of us. Let's make y be up here. There's my f of x and x-axis along there. I'm going to call this one point I've marked off for x as a, and that one out there is going to be b. And I want to imagine a function that when x is a, just lands right there. Right? So we'll say, oh yeah, the y value for that, you can find it by putting a into the machine. There's f of a. Okay, right at that spot. And then at b for x, I want to imagine it's going to line up with that little y value mark. Okay, I want to imagine it hits right here. So that'll be up here at f of b. Okay, so those are some y values. F of a is just a y value, and f of b is a y value. And what I want you to do is pick any y value you want in between this first y value, in between here, and this last y value in between there. Just pick a spot and just kind of locate it with a little arrow. I'm going to go right here. Right? Doesn't even matter where you put it, as long as you put it in between. That particular y value, hey, for today, for my notes, I might say, hey, let's call that d. Okay, and it's going to be some number stuck in between f of a and f of b. So here's my challenge to you. I want you, well, maybe take a ruler and let's just kind of mark this across like that. And now you're going to draw a function from blue dot to blue dot. But the catch is it must be a function, so it has to be continually passing the vertical line test, and it must be continuous. So this in-between y value rule applies to things that are continuous. And I want you to try to go from that blue dot to that blue dot without hitting that orange line at least once. You can't, right? This is the rule. So you're like, okay, I don't want to hit the orange line, right? At some point, you have to hit the orange line. You might even hit it twice, but you're going to hit it at least once. Okay, so mine hit it 3 times. And all this rule says is, yeah, if that y value is in between the ones on the ends, you're going to hit it once. So the rule might be written like this: a function f of x that is continuous. I mean, there's no guarantee if it's not continuous, but if it's continuous on some closed interval from a to b, so these little square bracket deals here, when you draw that, that's a shorthand way of actually saying this. A is less than or equal to x is less than or equal to b. That's all that means. You're going to find that that function takes on, I'm just going to put this in everyday common language first, every y value from f of a to f of b at least once. So it hits every single orange line that you might draw in there at least one time. Mine actually hit 3 times there. Now, the notation you might see written a little more formally says, if y equals d is in between that f of a and f of b, then there exists, right? This is what we call an existence theorem. It doesn't tell you how to find it. It just says, don't worry, don't lose any sleep. It will be there somewhere. There will exist some sort of x value, let's call it c, such that we do actually have this collision between the two things. F at c will actually hit your orange line d. So maybe for me, that might be my x is equal to c. There's going to be one spot where if you figure out what that blue f of x is doing, yep, at that spot it's going to hit your orange line y value. It does not tell you how to find it. It just says, well, it's there somewhere. So we're going to finish up with this example. These questions using theorems are a little bit weird because sometimes you won't even find answers, but you'll just say, well, I know it's there. And so this one says prove, right, in math court, prove that there exists, somewhere out there it happens, there exists at least one number that is exactly 1 less than its cube. And I'm looking at that going, what? What are you saying here? A number that is exactly 1 less than its cube. I don't even know what that's trying to say. Let's just pick numbers and see if they work. I don't know, like 2. Okay, there's a number. Is that good? Well, the cube of 2, okay, it says it's cubed. 2 cubed, that would be 8. And so it's saying, hey, is the number 2 1 less than its cube? No, not for 2. 2 is 6 less than 8. Okay, so it's not 2. Maybe it's 5. Maybe it's 5. Well, 5 cubed is 125. Well, that's no good because 125 and 5, they're like 120 apart. Maybe it's 1. And you can spend all day trying to find this answer, right? Well, 1 cubed is 1. Is 1 1 less than 1? No, 1 actually equals 1. So I haven't found any answers yet, right? But I don't have to. It just says prove that it exists, that it's out there. So I might do my proof like this. I might say, well, let's say there is a number, and let's just call it x. That's like these numbers right here. Well, these ones over here, that would be the x cubed. Okay, so x cubed is equal to its cube. And they're not supposed to be equal. The cube is supposed to be 1 bigger than the original number. So if I wrote this down, this would be a lie, right? They're not supposed to be the same thing. The cube is supposed to be bigger than that one. So the right-hand side's already too big. Let's help the left-hand side out. There. If x is 1 less than the cube, let's add 1 to it. Then we can actually have some equality. You're trying to solve that equation. And that's hard because it's cubic, right? You know, you could try putting everything over to one side. Hey, that works for quadratics. You could say, well, x cubed minus x minus 1, that would have to equal 0. And I'm kind of stuck because I don't have any cubic equation solving skills. But I could do this. I could say, well, let's try to imagine there's some function. You know, I guess you could go to your graphing calculator if you want to find this answer, but I don't even want to find it. I just want to prove to people that it exists. So that function needs to hit 0, right? This is what I'm wondering is, hey, do you ever equal 0? Well, let's just draw a quick little sketch. I'm not even going to use my calculator at all. And I'm going to try to address this question. Okay, so here's what I'm wondering, kind of in math court. Does f of x ever equal 0? Because if it does, then there is an answer. Okay, well, let's see if we can prove that it's going to have an answer without even finding the answer. That's the weirdest thing. I'm going to prove it has an answer without even finding the answer. And I'm not going to do a lot of graphing. So here's going to be f of x. This is going to be x. And here's one of the things I noticed. So yeah, granted, you have to play around a little bit to notice things like this. But I noticed that at x is equal to 1, it doesn't actually work. Right? I even tried it up here, right? 1, the cube is 1, they're equal. If I try looking at my function, x cubed minus x minus 1, if I put 1 into that, I actually end up with an answer of -1. Not 0, not the right answer. But if I put x equals 2 in, okay, 2 cubed is 8, minus 2 would be 6, minus 1 would be 5. Okay, so that is up here at 5. Quite have that in line there. Make that a little better. There we go. I'm not necessarily trying to find the answer. Maybe there's a few answers. I don't know. I'm just trying to show that there's at least one out there. Well, this graph would have to hit 0 if there's an answer. But this function that I'm looking at, this thing here, it's just a beautiful polynomial. They're always continuous. And so this theorem says, well, it has to be a continuous function. Yeah, it is. And let's go and look at an interval. Let's go and look at the interval. And people might write the interval like this, kind of a short notation to write it, from 1 all the way up to 2, including 1 and 2. That's what the square brackets mean. Does it happen in there? Well, I challenge you to go from that dot to that dot without going through the x-axis. I don't know, like, does it wobble around? I don't know, but you're going to have to cut through and hit every value in between -1 and 5. I'm wondering, does it ever hit 0? And the answer is yes, once. So if people are like, well, could you prove this? There, I just did. I could say there exists an answer. I don't know what it is. This is the neatest thing about these theorems. I don't know what the number is, but I know it's there, and I know it's somewhere in between 1 and 2. You can go find it if you want, if you have the skills, but I only had to prove that it exists, right? And so this theorem, like all of our theorems, it's just going to be an existence theorem. It says it's out there, somewhere between 1 and 2. And now you can sleep well knowing that it's there. And so if you like that kind of lawyer math thing combination, you'll love when we work with these theorems. And that's the first of 3 or 4 theorems that we're going to look at. And that finishes up our lesson for today.